طيب بسم الله الرحمن الرحيم. We started talking about chapter 2 symmetric cryptography. We talked about the different types of cryptographic techniques from the perspective of the operation, whether it's transposition or substitution and so on, whether it's symmetric key or public key cryptography, whether it uses like one key or two keys, things like that. Then we talked about the different types of attack based on the assumption whether the attacker knows only the ciphertext or he knows the ciphertext and some of the plain text, or he knows both, and so on. Then we started to talk about the fuzzy structure. Fuzzy structure, which is recommended by NEST as a critical structure for achieving symmetric cryptography. And we talked about the different characteristics that affect the properties of the fuzzy structure, starting from the block size. So the block size itself, the key size, and so on, all the way until we talked about the ease of analysis. And we said that modeling the fuzzy structure as two like recursive equations makes the analysis really easy to understand, although it's very hard to break. And that's the good objectives that fuzzy structure try to achieve. So today we'll start to talk about the first symmetric cryptographic technique in the category of block ciphers, which is the DES, or data encryption standard. So data encryption standard was the first symmetric cryptographic technique that NEST has recommended. Later on, of course, they recommended the deprecation of DES, and we'll talk about why. And they came up with what we call triple DES, okay, instead, to try to make it harder to break. So today we want to discuss the DES, how it's structured, and why we need to introduce triple DES and deprecate DES. And eventually we'll talk about AES as an enhanced technique that tries to achieve the same objective of triple DES, but with a lot less complexity. Okay? So, as we said, DES was the most widely used encryption scheme until the late 90s. NEST later on created or recommended what we call the algorithm itself is referred to as data encryption algorithm. So, the algorithm itself uses a block, as we said, this is part of the block ciphers. So it has to work on a block, unlike the stream ciphers, which we will talk about in a later stage. So this takes a block size of 64 bits. So the block size is fixed. So if you have very large plain text, you need to first divide it into 64-bit blocks, okay? And then apply the algorithm on one block at a time. In a later stage, in the end of this chapter, we will talk about some pipelining as well, which we call it mode of operation. So we'll talk about that. So anyway, the key size is 56 bits. And this is one of the weaknesses of this algorithm, really, because when we talk about the analysis of this algorithm, طبعا we'll not go deeply into the analysis in terms of information theory, but the algorithm itself is good, is powerful and everything, but the problem is the key size is very small, okay? Making the brute force techniques really possible using nowadays devices, okay? So 56 bits, we talk about 2 to the power 55 guessing on average, which is possible to be done in a short amount of time given the computational capabilities that we have nowadays, except for quantum time. The structure itself is mainly based on the fizzle structure. Okay, so as we will see, it's quite similar. All they did is that they built some envelope around the fizzle structure, and they have defined arbitrarily the round function, because we said that fizzle structure is based on it uses this round function as a black box. It does not really define a specific function inside it. It's left to the developers to develop whatever round function they see appropriate. Okay. So the process of decryption is essentially the same as the encryption, but in the other way around, as we will see. The strength of the DES algorithm, there are certain concerns, as we will talk about. There is some concerns in the algorithm itself, okay, but not it's not to say that it's weak. The concern here is more towards the implementation of the algorithm, because it uses bit level manipulation, okay? So it makes the algorithm only feasible as hardware implementation. It's not feasible as software implementation, and you will experience that in the development assignment later on. But more importantly, the concern is coming from the fact that the key size itself is very small. 56 bits, it tends to be small given the computational capability that we have nowadays, because it makes the operation like 2 to the power 55 possible guesses using brute force. Of course, there are well-established key guessing algorithm which actually uses or tries to be as smart to avoid all the exhaustive combinations, making choices less than 2 to the power 55. And that makes the attack time even shorter. And for DES, it's easily breakable, okay, using moderate type of device, even cell phones. So this is the structure of the DES algorithm. And as you can notice here, this is the fuzzy structure, exactly. So this is exactly the fuzzy structure. Okay? The only thing that they modified is inside here, there is the round function, which we will talk about. Okay? But the structure itself has been used as is. They just put an envelope, like one step, one initial step and one step at the very last step. And this is called initial permutation. Okay? By permutation here, we mean that the bits can be, exchanged its position at the bit level. Okay? So this permutation is done arbitrarily. This is actually this is the initial permutation, which is done here. And this is the inverse initial permutation, which is done here. Okay? Of course, these permutations, you don't have to memorize, obviously. Okay? But these are done arbitrarily. Okay? And these are fixed. Okay? So they don't change. These are fixed and publicly available. Okay? So the assumption here is that doing this initial permutation and inverse initial permutation, it will increase the strength of the DES algorithm using the fuzzy structure. Okay? The other thing that we need to notice here is that we talked also about the fuzzy structure, that part of the fuzzy structure, it has what we call the sub-key generation. Okay.
So how does it strengthen the DES as it's fixed and it's well known and it's public?
The fuzzy structure. It actually introduces these envelopes supposedly to strengthen the robustness of the DES algorithm using the fuzzy structure. Okay? So the idea here is that by incorporating the fuzzy structure inside the DES algorithm, we can leverage the chips that have been fabricated to provide this fuzzy structure. Okay? So they have leveraged all the hardware design that has been done on the fuzzy structure. Okay? But they added to it this envelope or this initial permutation and inverse initial permutation. That's it. The sub-key generation algorithm was not defined by the fuzzy structure. It's similar to the round function. Okay? So this introduced its own sub-key generation algorithm based on 3 steps. The first step is called permuted choice 1. Okay? Permuted choice 1. And then we do some left circular shift, and then we do permuted choice 2. One thing to pay attention to here is that this permuted choice 1 is done once for all the subkeys, as it's obvious here. Permuted choice 2 is to be done on the level of each subkey. Yeah, it's obvious, right? Type. The other thing that we need to pay attention to here is that permuted choice 1, we call it permutation with contraction. And what that means is, now we said that the key size is 56, right? Right? What is the key size here? Okay, so where does this come from? This came from the 56 bits will be padded first to become 64, and then the 64, okay, will become here 56 again. Okay, we call this permutation with contraction. Okay, so it's not like this. This permutation with no contraction. Okay, so we have three types of permutation. We have permutation with contraction, permutation with expansion, and permutation only, which does no effect on the size of the input data. Okay, so this permutation choice 2 is permutation with contraction. So it contracts the 64 bits into 56 bits. And then we have another permutated choice 2, which is another permutation with contraction, and it compresses the 65 to 48. ماشي كده؟ Okay so far?
Compressing means here
Compressing يعني.
to delete some.
Not to delete. يعني أنت you can مثلا you can map 2 bits into 1. Okay? Using some XOR, any logic, things like that. Okay?
يعني الأكشوال key profile اللي بيستخدم في الانكريبشن 48
Or for each round. The actual key that's used as part of the algorithm is 56.
Is there any relationship between the 48 and the number or the size of the plain text?
The size of the?
The plain text?
Yes, there is. Yeah, هنشوف بقى طبعا يعني ال 48 bits will be input to the round function. Okay? The round function, as we have discussed before in the physics structure, it divides the input plain text into 2 parts. Each part is 32 bits, right? So the round function has 32 input and 48 key. Okay? And it's supposed to produce an output, which is of course 32 bits as well, right? Given the physics structure that we talked about. It's the part here. Okay? So this is how it looks like. So we have the 48. So this is so this 48 will be, so 28 and 28, this is 56, sorry. And 56 will be again contracted to become 48. And this 48 will get input to the round function. The round function here takes 32 bits, okay? And what it does is that it does what we call permutation with expansion. Permutation with expansion. ماشي? Permutation with expansion, the output will be 48. And here, what we do is a Vernam cipher. Remember, the Vernam cipher is just XOR. Okay? And even with XOR, we talked about the strength of the Vernam cipher before. We said the Vernam cipher, assuming the cipher text only attacks, it's very powerful. The problem is if you know only one plain text. If you know only one plain text, you can guess the key على طول. Okay? So what we are doing before and after is just to confuse the attacker from being able to get the plain text and get anything out of it. So even if you know many plain texts and cipher text, you're still not able to guess the key easily. Okay? طيب. So here بقى what we do, خد بالك هنا بقى it's not a permutation of contract. Here what we call it's called a substitution. And by substitution here we mean that we take the 48 bits, we divide it into 6 bits times 8, ماشي? And each 6 bits, okay, will be used to look up some 4-bit value from a lookup table. ماشي? From a lookup table. ماشي? So if each 6 bits will be mapped to a 4 bits. Okay? So unlike permutation with expansion, this is called substitution. So there is a lookup as part of it. ماشي? So we do the lookup table, we do the lookup, and we convert each 6 bits to 4 bits. So the result will be, it's like some kind of contraction. So the 48 will become 32. ماشي? Blocks of 6 bits, each you have 8 6 bits blocks will be converted to 8 4-bit blocks. So 4 times 8 is 32. So the result here will be 32. And then we'll do another permutation. And this permutation is no contraction, no expansion. So it preserves the size. ماشي? Okay? And then we'll do the XOR, which is normal to finish this round, and then we go to the second. So all of this is done per round. You have 16 rounds like this.
The table, this is public or?
Yeah, the table is public.
It's no.
All types of substitutions, by the way, which we will talk about in all algorithms, and the structure of the algorithm, and the lookup tables are all public. ماشي?
The permutation itself, is it public also?
Yes, it's public. Yes, permutation is public. Yeah. Supposedly, by doing this permutation, you still make it hard because what's not known here is the key. Yes. So the main objective here is by doing all of this, you make the ciphertext, okay, has absolutely no correlation to the plain text in any way. ماشي? So that's what we are trying to do here. Because if there is because Vernam cipher, it preserves this correlation. يعني just the Vernam cipher, we do XOR. ماشي? You do XOR. So by knowing only one plain text, خلاص, you can break and guess the key. خلاص. And guess the key once, معناها the whole communication is broken. Right? But here, what we're trying to do is to make no correlation whatsoever. If you look at the plain text, it has no correlation whatsoever to any kind of guessable plain text. That's the main idea. Of course, in order to prove this mathematically, you have to get into some information.
So the plain text and the ciphers has no direct relation.
Yeah, to the input in any way. In any way. Because if there is a way that you can correlate the ciphertext to any kind of guessable plain text, what does that mean? This means that, مثلا, you know that the text is in English, okay? So is there any kind of correlation? If you look at the ciphertext, can you guess any kind of plain text that corresponds to it in English that looks like a readable sentence? ماشي? Vernam cipher does not actually achieve this objective strongly. And that's why, as we said, if we know one plain text, خلاص, you broke everything. Okay? And as we will see, based on that objective, actually, sometimes the encryption algorithm can be used as a random generator. Because the main objective, again, for random generators is to make the output, okay, as we will see, it has no proved correlation, even with each other. Yeah, it's unpredictable. خالص. Okay? But the main problem here is that, the main difference here is that the key ده هو the most important. إنما الالgorithm itself is public. Everything is public. Okay? Okay? طيب. Some properties بقى that we can really observe. اتفضل. Yeah, the key size is fixed and the block size is fixed.
And also
Yes, of course. Yes, all the specs about the algorithm itself is publicly available and it's fixed. Even يعني round function here is well known. It's not like the fuzzy structure. Fuzzy structure left it up to the developer. Here لا, خلاص everything's clear. One important property here is you can imagine the amount of bit level manipulation, because this was one of the main weaknesses of this algorithm, okay, that made this algorithm really feasible only using hardware implementation. Because as we all know, the bit level manipulation is always very hard using software. Okay? So in software, we don't have even data type called bit. The least we have is unsigned int, اللي هو unsigned int, or اللي هو ال 8 اللي هو 1 byte. صح? We don't have a data type called bit. Okay? So really manipulating bit level in software is expensive. It's possible. And they do some tricks to do this, to work around this, but it's expensive in terms of software. But in terms of hardware, as we all know, it's very powerful. Hardware is very powerful in bit level manipulation. Okay? So this is one of the main properties of this, but in the past this was okay because they can really implement chips, the hardware manufacturing companies, they can really build very optimized chips based on that, but that makes everything rigid, not dynamic, it doesn't change, and that's why actually until today, DES and triple DES are still being implemented in some devices, even though we know now that they are breakable easily, but they are still being used. Because it's hardware, it's not easy to change. Okay? Type. So these are the specs of the algorithms that we will talk about. Not only this, but also AES, and we'll talk about the motivation towards AES in a bit. So in this, we know that the key size is 56, the data size is 64, and of course the number of alternative keys is actually 2 to the power 56, but we can possibly make guesses half this number to get to the key, which can take around 2 to the power 55 number of trials before we get to the key. And using nowadays devices, we can do this in an hour. Imagine? Still, somebody might argue, typically if we do this in an hour, we can change the key every hour or less than an hour. In that case, this can still be usable. صح? Okay? Because we said that even if we can break the key using a duration of time more than the lifetime of the key, then the attack has no meaning.
That's possible.
That's possible.
Because since it's a hardware implementation, it's possible to change the lifetime of the key.
It's changing the lifetime of the key is part of the protocol. Here we're talking about the mechanism. It has to be part of the protocol بقى. The protocol is the one that controls when there is a renewal of the keys or something like that. This is part of the protocol because, as we will see, there is a technique for key exchange. Okay? So depending on when you decide to renew the key, this key exchange has to be triggered in order to renew the key. Okay? Anyway, so changing the key is part of the process, part of the protocol or the security service, not the mechanism. The mechanism is this is the technique. Okay? Type. Assuming that AES, we didn't talk about AES yet, we'll talk about it. So AES came with some motivation that, okay, so we need to have security strength, which is more than this, yet it's less complex. And we'll see about how we achieve this using AES. Assuming that the key size is 128, so we need 127, so this will give us how many years? Huge amount of time. Yeah, because it's exponential, remembering. By increasing 1 bit, we double the time required, because it's exponential. صح? طيب, which is good. But of course, affecting the key size or enlarging the key size affects what?
The speed.
Complexity, yes, complexity. صح? Complexity. يعني all the structure that we talked about has to be يعني more complex in order to accommodate the large key size, obviously. صح? طيب, that's why بقى AES tried to reduce the complexity, because they said if we increase the key, we will increase the complexity. So if we reduce the complexity of the structure itself, this makes the large key size more feasible to be implemented. And not only to be implemented efficiently, but it's command implementable using software.
Does the AES has the same production?
Block size يعني?
Hardware.
Yeah, the AIS is actually efficient in hardware and software. We will talk about it, don't worry, we'll talk about it. Triple DES is nothing but 3 stages of DES. And that's why it's actually the key is 168, which is 3 times the 56, simply. So all we need is just to have a key size of 3 times the size, and then we take the first 56, we apply DES, we take the second 56, we apply DES, okay, and so on. That's it. But we apply it to the same plain text. Okay, we'll see how this is done. By doing this 3 times and increasing the size of the key, the good thing about this is that now we can use the same hardware but replicate the chip. واضح? So that was the workaround, or the dirty workaround that they found. Okay, so we can use the same chip 3 times. Okay, عشان to make it stronger to break. Okay, and more complex to guess because of the key size. And still, it's the hardware. We can replicate the hardware 3 times. So this will make the development of triple DES faster. Okay. Luckily, طبعا, we don't have to implement it في assignment in hardware, so I will be able to do it 3 times in software very easily. But again, you will see that the bit level manipulation makes the algorithm really, really slow. ماشي? The good thing about AES بقى is that it's actually flexible command to the number of bits of the keys. So we can have 128 AES, 192, or 256, which increases طبعا obviously the amount of time required to attack, which is good. ماشي?
Professor, is the constraint is the complexity of the algorithm, or
هو they found that يعني this was working fine and it was fast enough because of the fact that we use hardware, so that was good. However, they found after some time that guessing number of choices for the key is actually doable because the computational capabilities of the devices nowadays is actually increasing. ماشي? So they found that the structure itself and the key size is actually weak. So one dirty solution, as I said, is just to replicate the hardware 3 times to do triple DES. When they did this, it was fine because it takes a very, very long time to guess the key, which is good. But look at the complexity بقى.
what makes
We actually triple the complexity as well.
what makes the AES more flexible?
احنا هنتكلم بقى لسه هنتكلم كلام. Okay. Well, basically, what I'm trying to say here is that what makes DES and triple DES really feasible only in hardware is the bit level manipulation. Okay? So we need to avoid حتة بقى الايه البit level permutation lookup table using 6 bits يعني. Okay? So if we make it byte level, and we'll see بقى how, if we'll make it byte level, if we use some kind of operations which are optimized in software as well as hardware, such that مثلا matrix multiplication, we know how to do this matrix multiplication using software and hardware. So if the operations as part of the AES, it uses some operations which are really efficient in software as well as hardware, this will make the implementation of AES more efficient. So this is triple DES. Okay, so they deprecated DES. Okay, and they came up with triple DES. And as you can see, the plain text goes through 3 stages of this. That's it. Okay? So the key is divided into key 1, key 2, key 3, and each of these keys بقى gets input to the sub key generation مش عارف ايه. كل ده اللي هو ايه؟ part of the this الواحد. Okay? One thing to notice here is that it's the keys are applied عشان برضو ده يعني one of the things that usually students they get trapped into when they do the assignment. The keys have to be applied in a reverse direction when you go to the decoder or the decipher. Okay, so you apply K1, K2, K3 at the decoder side or at the receiver side. You have to apply the K3, K2. ماشي? It has to be applied backward, yeah. ماشي? So the triple this is nothing, yeah. But the good thing is that each of these is actually a hardware chip, so we can just replicate the chips in a chain-like fashion, and we can manufacture devices quickly. We don't have to change the chip itself, which is good. ماشي؟ طبعا يعني this is good. Triple this is was approved as the symmetric encryption by NIST as part of the FIPS 46-3 document. Because of the fact that the original disk, which was using the 56-bit key, was permitted under the standard, but it was found that it has some weaknesses, as we discussed, and therefore they recommended the extension or the upgrade to triple disk. ماشي? It is anticipated that triple disk and the AES will be the de facto standards or will be the standards to go for symmetric encryption in general. And as we will see when we talk about that security services and protocols in each layer, you will never see this being used in any of these protocols. You will see this, triple this or AES or RC4, which is stream cipher that اللي هو لا مش الاسيمتريك اللي هو الستريم سايفر. We'll talk about stream cipher. A key exchange? Yes, definitely. We will talk about it in a later stage. We'll talk about key exchange, of course. Here, the assumption is that both the transmitter and the receiver, they know one key. They share the key. How do they share the key بقى? We'll answer this question in a later stage. طيب in 97 بقى NIST بقى issued a call. هم بصراحة هم نفسهم كانوا puzzled شوية. They issued a call. قالوا يا جماعة احنا we need to have a symmetric cryptographic technique which has the same strength of triple DES but with a lot less complexity, and also we need it to be optimized in software as well as hardware. Okay? طبعا they had lots of proposals from people, okay? And the one that they selected was by Regenthal as approved, طبعا واضح من الاسم يعني, as the proposed AES algorithm, which was published in the FIPS 197, not that we care about the number. And these are the name of the developers, doesn't matter. So AES, this is the structure of AES. ماشي. Unlike this مبدئيا, AES uses 10 different rounds. As you can see here, it's 10 rounds. هتقول لي ليه ده 16 وليه ده 10? Okay, that's the proposal يعني. طبعا again, all of these are based on some يعني mathematical proofs واشياء زي كده we don't have to get to. The add round key here, these add round keys, these are nothing but Vernam cipher. يعني بس بناخد two inputs XOR. That's it. Very simple. ماشي. One thing to notice here is that the key itself is 16 bytes. مش هتلاقي بقى أي ذكر الفكرة يعني. There's no such word called bit here. There's no bits. There's no bit level manipulation in any way. Okay? So each of the rounds, طبعا this is the encoder side or the encrypt, and this is the decrypt side. Okay, so this is the encryption side and this is the decryption side. ماشي? So they are mirrored to each other. So each of the rounds is actually divided into 4 different operations. One is called the substitute bytes. And substitute bytes here, as we will see, again, it's byte level. There's no about 6 bits, and we look up 6 bits, we convert it to 4. No, we'll see. It's byte level. We'll take it based on hexadecimal digits, and we will look up in the lookup table, which is again public, okay, to get value and use it as a substitution. ماشي? To the substitute byte, okay, and then shift rows. And the shift rows is like, again, it's not a circular shift in bit level. Okay, it's byte level. Okay, so we just switch the byte to the left or to the right. We'll see how this is done, very simple. Okay, and then mix columns. Mix column is nothing but matrix multiplication. And we know how to do this. طبعا matrix multiplication is very powerful to be done in software or hardware. Okay, and again, add round key, which is Vernam side. So the operations themselves, they are byte level manipulation, byte level operations, normal byte level operations, which can be done in software or hardware. So at every stage here, okay, we have, عشان برضو when you see this in the assignment or anywhere, we have the concept of what we call state matrix. We have state matrix. The state matrix is the output at every stage. So we take this state matrix and then we XOR it with another state matrix, which is the add round key. Okay, the result will be a state matrix. Okay, and then we get the state matrix, we do the substitution, so the result will be state matrix and so on. So the state matrix is the output at each stage. We call it state matrix. There is a key expansion technique similar to the one in this. However, again, this is not using a permutation with contraction والكلام اللي احنا لا. This is using some key expansion techniques, okay, which works in the byte level, not in bit level in any way. ماشي? And this key expansion techniques generates an array of طبعا the key itself as a length is 16 bytes. 16 bytes, okay? 16 bytes times 8 is 128. ماشي? So we get this 16 byte and put it as a 4x4 array. So each item in this array is 1 byte. Okay? And then we use this matrix value in XOR if we want to XOR. We XOR matrix, we multiply matrix, and so on. That's it. ماشي? So we know how to do a matrix to matrix logical operation. That's very easy, done in software or hardware. Or matrix multiplication, and we will see that the state matrix gets multiplied to an arbitrary matrix, which is well known. And the lookup for the substitution is also well known. ماشي؟ واضح كده؟
Always in AES the key size is the same as the block size.
لا 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 ما حدش قال كده.
16.
لا 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 ما حدش قال كده. لا 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 لا. This is not necessarily the case.
And the structure of the plain text also in matrix, so it will be represented as a matrix, right?
Yes.
So we can change.
Yeah, the structure is matrix based, and the key itself is structured or is put as a matrix format, because we know how to deal with matrix format in software and hardware very powerful. Okay, we know how to do XOR, we know how to do matrix multiplication, all of them in software or hardware. ماشي كده؟ طيب. So this is the first state. طبعا the Vernam cipher is XOR normal. This is the substitute, and in the substitute, what we do is very simple. From the state matrix, which is the result after the add round key, the first stage of add round key, we get each byte. Each byte is nothing but 8 bits, and 8 bits can be can represent 2 hexadecimal digits. Okay, so we take these hexadecimal digits, we take the number here, so this is a 0 and this is 0, so the result will be here 63. So we put 63. Okay, this is fixed, it's publicly available. Okay, and same thing back, you get 3 C, so add 3, so this is 3 and C. You go here, EB, you put EB, and so on. Very simple. Well, and we keep doing that. So we come up, this is the new state matrix. So this will be the new state matrix. Okay? And then after that, the first state matrix is using the add round key. Add round key is just XOR. We XOR the key matrix with the plain text. Okay, just XOR. Well, that's why you say that it has to be the same. Okay, it has to be, the key has to be the same like the plain text, because we XOR and supposedly the XOR uses the same size for both. Yes, yes. So yeah, that's a logical way of thinking, but again, the technique itself does not really restrict this. يعني ماشي. We do the shift rows. Shift rows is very simple.
How is the first state matrix generated?
How they is?
How do we generate the first state matrix?
The second stage is a shift rows, and shift rows here again not bit level circular shift like this, okay? But here it's byte level. So here very simple. The first row, no change. Okay, the first row of the state matrix, no change. The second row, we will shift 1 byte, okay, to the left. The second row, 2 bytes to the left. The third row, 3 bytes to the left, which is 1 byte to the right. Yeah. And that's why here you see, okay, and because it's circular. Yeah. واضح كده? Again, very simple. If you apply this to the state matrix, the result here. So here it contains the same numbers like here, but rearranged. Unlike the substitution substitutes the value itself. ماشي؟ واضح. Then we do mix column. Mix column here is nothing but matrix multiplication. So we multiply, this is the state matrix. Okay? We multiply it by a fixed matrix. This matrix is fixed. Okay? And the result will be another state matrix. واضح؟ Steps are very, very simple. ماشي؟ The effect of this step on the strength, that's another story. ماشي؟ طيب. This is AS, and AS actually is proven to be efficient in terms of software. Again, as we can see here, there's no operation that requires bit level manipulation in any way. There's no permutation, things like that. Therefore, we can do this, and as you will see in the assignment, you can do this in software very easily, and it's very fast, very fast. ماشي؟ حتى with large key size of 128 and 192. طيب. طيب. Random and pseudo-random numbers بقى. These random number generators are very, very important, as we will discuss in the security services. These are being used in many ways to generate, for example, the key itself. The key itself is a random sequence. ماشي? So we need some random generators and pseudo-random. We'll talk about the difference between the two. ماشي? Such that we can use this random sequence بقى إيه in many things later on. For example, to use it as the key directly, or to use it as different things, as we will see. ماشي? Sometimes we use it to generate public keys, and then from the public keys we generate the private keys based on certain relationship. يعني we use it in many ways. We use that برضو to generate the symmetric key for temporary session keys in the case of Wi-Fi. Okay, and the idea is to get, in addition to, again, a key value, we have to append some kind of session level information, and from both we generate another sequence for temporary session keys, as we will discuss in a later stage. Okay. Okay, but what this tries to say is that random generators and pseudo-random generators are very important. Okay, what we need to discuss in this part is what are the conditions for these random generators to be feasible, to be used, okay, and what are the types of these random generators. The conditions are simply two, okay? So the first one is that the random sequence has to be random, and what that means is that the random sequence, okay, needs to have uniform distribution. بمعنى I cannot generate the random sequence at the end of the day. It's just like a stream of zeros and ones. Okay, so it doesn't matter. It doesn't make any sense to say that this random sequence will end up having 90% ones and 10% zeros. If you do this, okay, what message are you giving to the attacker?
It's easy to
Play on the zeros, right? Because the number of zero choices is much less. So if you play on the zeros, you'll be able to guess the key fast. صح? If it's reversed, I can play on the ones. I can play on the location of the ones. So in that case, I will guess the key fast. Okay? So the true random needs to have the same probability for zeros and ones. Okay? So this way, I'm maximizing the number of guessings to the attacker. Okay? The locations of the zeros and ones can be intermingled together in any way, but I need to have zeros and ones equally sized in the almost equally طبعا. ماشي? So that's the first condition. The second condition, ماشي? Okay, so the zeros and ones are almost equal. However, if I happen to get part of the key, only part of the key, okay, will I be able to predict the other parts based on knowing that? If that's the case, then that's not a good way of generating random sequence. If there is any correlation between the different parts of the key, again, the attacker can use that easily. So once I know this, okay, I can use it to minimize the choices to guess this and so on, because there is a correlation. صح? So it would be good to have no predictability from the different parts of the key.
So should probabilities be independent?
Yeah, this is what it means. So the different parts of the key are statistically independent. Okay? They have no they have no correlation. Okay? There is a metric that NIST has actually proposed that measures the correlation between the different parts of the key, and they do this correlation on a bit level. The correlation of the ones and zeros, يعني if you consider one, correlation on one and zeros and zero actually reduces to the first one. And what is the probability of having zeros? Probability of having one. ماشي? But if I have مثلا 1 0 مثلا, okay, does that mean that the next two bits will be 0 1? Do I have this pattern repeated? If there is some repetition of this pattern, this means that there is a correlation between 1 0 and 0 1. So in that case, it will not be a true random sequence. واضح كده? So so NIST has actually proposed a set of metrics which tests, they call them tests. Okay? So for example, you can first calculate the number of ones and number of zeros. They have to be equal. Okay? Calculate the number of 1 zeros and number of 0 ones and number of 1 1 مثلا. Because if I have مثلا the number of ones and number of zeros are equal, okay? But I have 1 1 1 1 1 1 1 0 0 0 0 0. Is that considered to be a random sequence? لا طبعا. It's not a random sequence. Because if I know just 1 1, I can repeat that many times. Then I can guess half the key in no time. That would not be a random sequence. واضح? So NIST has actually proposed certain well-defined metrics to really apply on any random sequence to know that it's indeed random sequence. These tests are very well known publicly يعني. ماشي؟ فهمنا كده؟ So these are the two that based on which I can say that. So by randomness I mean uniform distribution. Okay? So if I calculate, if this is the key, if I calculate the probability of 1 and probability of 0, مثلا, I see that it's the same. The probability of 0, 1, probability of 1, 0 is actually the same, and so on. ماشي? So the probability of any pattern is actually the same.
The key generator, this is a random key generator.
ما احنا we'll talk about the types of the key in a minute.
So it generates a series of keys, right?
It generates a random sequence.
Sequence of keys.
Sequence of bits.
Bits,
Okay.
For a key.
Take back these bits. Take these bits. اطبخهم. I don't care. Okay. What I need is that to generate a random sequence. Okay. This is the objective. ماشي كده? So the second one is independence, which implicitly means that they are statistically uncorrelated. So the different parts of the key are statistically uncorrelated. Okay? By knowing one part of the key, I cannot guess the other parts. واضح النقطة دي؟ واضحة؟ تمام. اتفضل.
لو استخدمنا نفس البلين تكست.
نفس الايه؟
بلين تكست.
لا ماليش دعوة بالبلين تكست هنا. هنا I don't care about the plain text. خد بالك انت some of you are still confused between the random generators and the encryptor, the ciphers. Those are two different functions. Okay? Ciphers, they take input key and plain text and produce ciphertext. Okay? Random generators, they can take nothing. They can take nothing. Okay? They produce random sequence. My objective is when I see a sequence, okay, I need to be able to tell whether this is a true random sequence or not. In order to say that this is a true random sequence, I need to apply these two conditions. And I need to perform all the tests that NEST has recommended. Okay? If all the tests pass, then I say that this is a random sequence. طيب بعدين خد بقى this random sequence you can take it and use it in any way. أنا مش دعوة. ماشي؟ We use it بقى in many ways. طبعا حتى احنا في السوفت وير we use it a lot.
OTP is a random number.
The what?
OTP.
OTP is random numbers, keys are random numbers. We will talk about something called initial vectors, seeds, things like that. يعني we use it in many, many ways. We will mention this very commonly. Okay? طيب, unpredictability here in applications such as reciprocal authentications. Reciprocal authentications, we'll talk about this in the next chapter. It's like two parties are trying to generate, so each of them, they have to authenticate themselves to the other. You need to confirm that you are talking to Amr. Okay, so in order to talk to Amr, we have to generate some مثلا sequence, and for some reason this sequence happens to be the same on both sides. If مثلا the key مثلا the key, now we know the key, both we know the key اللي هو based على symmetric encryption. Okay, we can take this key, we can generate a random sequence based on the key, but in that case the key will be used as a seed for the random generator. Okay, or creating some kind of a puzzle, we will see. And then on the other side, if I can generate the same puzzle, then this is Amr, because صح? Because the puzzle embedded in it the key, which refers to my identity, because no one else knows the key but me and you, or any kind of مثلا of shared information between me and you that I can embed in the message to tell you that this is Amr and no one else. So if you can solve this puzzle and come up with the same result, then you know that you are communicating with Amr and no one else. We'll see this in, يعني, with many examples in a later stage. And for that we use the random sequence. ماشي? But the key thing here is that if I can use part of this key, or مثلا, or even I take the random sequence مثلا generated by this random generator, and I can take part of it and I say this is the key now. Okay, and then after half an hour I can take the second part of the key, okay, and say this is the key now. صح؟ مش احنا قلنا the key has some lifetime, so I can initially have a big random sequence, and then I divide it into parts. I say this is the key at time 0, this is the key at time t1, this is the key at time. طب ما هو the key at time t0, if it's broken for any reason, and I renewed the key, and there is some correlation between the new key and the old key, then I'm making things easy for the attacker, صح? So that's what we mean by unpredictability. So even if one of the keys, which is part of the random sequence, has been broken by the attacker, even if that happens, he will not be able to guess the second part of the key and the third part and so on. It will be hard for him. واضح? So this unpredictability is very, very important. ماشي? So that's what this means. طيب, what are the different types of these random generators? Some random generators, they take nothing. They take nothing. ماشي? Just some source of true randomness from the environment. ماشي? And they just convert it to binary. That's all what it does. True random source of an example. اللي هيقول لي example هنا بصراحة يستحق بونص. إيه؟
Can take heat of the processor, sometime noise, sometime, or my case quantum natural phenomena for one true source of.
I'm not sure if the heat of the processor would be a random source بصراحة, because يعني if you have a CPU with certain
In Linux,
in Linux,
yes,
maybe yes.
I heard from Professor Hotel.
Okay. Okay. هو sometimes, by the way, the random sequence itself will not يعني إيه will not be 100% random. So there are certain techniques that can be applied on a semi-random sequence to convert it to a true random sequence, and we do that. What do we call it? المهم يعني a source of randomness is sometimes the wireless channel. Wireless, yes, the wireless channel. Wireless channel is considered one of the true random sources of random sequence. Okay, why? Because طبعا typically in a typical room, ما تقوليش in a vacuum. In a vacuum, the channel is fixed. But in a typical room like this, you have a random process. The channel itself takes the channel gain and phase and so on. It takes a random process. It's a true random process. So that's why we have the field of physical layer security. Physical layer security is actually a whole field which emerged based on the fact that the wireless channel has some random characteristics, okay, which allows us to not only create a random sequence, but also to exchange key in a very simple way. Why? Because the channel between me and you is very unique. The random channel between me and any one of you is actually unique to these two parties only. Okay? And if you take the channel between each pair of people here in this class, you will find that it's unique. From one to another, it's very unique. Okay? So we can, in fact, estimate the channel gain and phase and so on between each two people, okay? And then convert that to some binary bits, okay? So the bit sequence in that case, even if it's semi-random, we can apply certain techniques to make it random, and then we can use it as a sequence, and from that sequence we can not only use it as a key, we can also, we assume that we have a shared key. Because the wireless channel is also reciprocal. Reciprocal means that if I estimate the channel between me and Ahmed, and Ahmed estimates the channel between me and him, we will have the same value. Okay? But if you try to do the same thing with anyone in the class, you will find it different. So the channel itself is reciprocal. So that's an example, okay? And that's that opened the whole field of physical layer security, which we have nowadays. Of course, this is a very, very big field, by the way. ماشي؟
What if we have eavesdropper between the 2 points?
أيوة this is based on the fact that the eavesdropper will have a different channel.
Even if
Yeah, طبعا.
listening to the channel?
طبعا. Even if he is listening to the channel of the eavesdropper to the transmitter is different. Okay? So that's the assumption. طيب. Another thing which طبعا the true random sources sometimes is not available in all applications. Another set of applications, especially in software, we commonly use what we call pseudo-random generators. Pseudo-random generators, they don't use a true random source from the nature. What they do is that they use a seed, and this seed is like a key, okay? And then they apply a deterministic, not a random algorithm, a deterministic algorithm, okay? Which generates the bit sequence based on the seed.
The whole point in the 3 types is that the 2 parties of the communication will reach the same key.
لا هنا أنا بقول لك this is the first type. لا
But even the
forget about changing the key. Here our objective is not to change the key. ماشي? Here what we need to do is to generate a random bit sequence. Okay? We can generate this random bit sequence by using A to D, okay, based on a true random source from the nature. One example, I'm just giving you this example, hopefully not to confuse you, but only to give you one example of this from the nature.
Sometimes we put the name, people want to put the name of the file, like the current timestamp, so it is just unique because
لا, but the current timestamp usually is being used as a seed, not as a random sequence on its own. ماشي? It's used as a seed. The timestamp sometimes is used as a seed. And by that, we have a deterministic algorithm which produces a random sequence based on the seed. هتقولي, does that mean that if I know the seed, I know the random sequence? Yes, because the algorithm itself is deterministic. Okay, but assuming that you don't know the seed, or if you know the seed, this means that خلاص, if both parties they know the seed, this is like a key that they exchange. So they will be able to generate the same random sequence both ways or on both sides.
How do you get the seed? How do you determine the seed?
Arbitrarily.
Randomly?
Oh, you can specify any seed. براحتك.
So it's
You can use the timestamp as a
based on
seed.
the user
You
or-
can use a very hello world. You can use it as a seed.
So it's based on the user.
Yeah, it's up to the user. Yes, up to the user. But the key here is that the bit sequence that gets generated will have the 2 conditions that we talked about. واضح؟ ماشي؟ So theoretically بقى, we can use here, again I don't want to confuse, but we can use here the encryption algorithm as the deterministic algorithm. Okay, but we have to apply the 2 conditions on the output. Okay, and the assumption here is that if we apply the 2 conditions of the random generator or the random sequence on the output from the cipher or the encryption algorithm, the 2 conditions will apply, and in many ways it applies. Okay, but remember here, the difference here in random generators, they don't have to be reversible. Yeah, طبعا encryption requires decryption. There has to be some encryption and decryption, so there is like some reversibility. Here I don't have. My objective is basically to generate random bits that look random. That's it. مش دعوة بقى if it's reversible انت خدها اعمل بيها اللي انت عايزه. اتفضل.
So if 2 people use the same seed,
Right.
they will get the same.
Man, that's allowed, yes, because the algorithm itself is deterministic. But the output fulfills the two conditions that we talked about.
Isn't this a weakness? Like if I know like
If you know the seed, yeah, it's a weakness.
if I know the
Yes.
person, I'll know the seed.
طبعا. And that's one of the reasons that, as we will see later, that some of the wireless security protocols which have been يعني standardized كمان. يعني there is a very simple assignment that they give to undergrad students to break that wireless and to know the key and know everything. اللي هي the passphrase that we use for our wireless password. Okay? Some of the security protocols in wireless, you can guess this passphrase in no time. There is an assignment, I can give you this assignment. I thought about giving it to you, but it's actually very trivial, yeah.
Without seed,
With-
deterministic algorithm cannot work.
Yeah, deterministic has no meaning. Without the seed, it has no meaning because it's deterministic. So the output that it will produce is easily guessable. يعني has no meaning. يعني.
The algorithm decide the seed itself.
Yes, ممكن. Yeah, you can do that. As you said, you can use the timestamp as a seed. And the seed, على فكرة, it can change, but it has to be part of the protocol. If I want to have the same random sequence at the transmitter and at the receiver, then they need to have the same seed. صح?
At all cases, it will provide the same key using the same seed. At all cases, it will never the key will never change if you're using the same seed.
وبرضه أنت you are mixing up key with seed. The key is used for encryption and decryption.
No, a random number or random
Generated.
random generated
Right.
thing that will come out of this.
Right. Right.
It will be always the same at all cases if we're using the same seed.
لا, it will be, as we will see, the random sequence can have variable size. So if you start with the same seed, apply the same deterministic algorithm on two nodes at the same time, they will generate the same bytes. Okay? They will generate the same bytes. Both of them use the same seed and the same algorithm. صح? Both of them, they will generate the same bytes, the same sequence of bytes. Okay? But that doesn't mean that these sequence of bytes are fixed. They are variable. But they start from the same seed using the same algorithm. And the algorithm itself is deterministic. Okay? So they will generate the same byte sequence. Okay? So that's why sometimes, by the way, we can get this random sequence and then rearrange it مثلا or do anything in such a way that does not break the two conditions, okay, to generate a different random sequence. You can do whatever you want, but anyway, the output has to fulfill the two conditions. So there is another one called the pseudo-random function. Sometimes we use, in addition to the seed, we use context-specific values. And these context-specific values, يعني أنا كtransmitter and receiver, we have the same seed. Okay? But in addition to the seed, we might want to use مثلا إيه؟ يعني أنت مثلا you are exchanging your credentials with a server. Okay? So the server has your user ID and password somehow, صح? And you have your user ID and password somehow, right? So you can exchange, طبعا you know the user ID and password, so we can use the user ID and password in addition to the seed to input that to a deterministic algorithm again, okay? So in that case, it's not only the seed, it's the seed in addition to that, there are some other parameters. Could be timestamp, but not to be used as a seed. These are fixed values, ماشي? These are fixed values, okay? In addition to the seed, we can use it using the deterministic algorithm to generate them. This is actually very commonly used in all the protocols that we will talk about in part 2. All of them, they use this pseudo-random function because we have many context-specific values. So,
it seems like the first type of the generator is the strongest, I believe.
The first type?
Yes, the simple.
yeah, but sometimes it's very hard to deal with. It's very hard to deal with. Yes, it's very hard to deal with. because we will talk about RC4, the stream cipher, and you will see that this pseudo-random, it's because we have to use it as a key, and the key is derived from some random sequence. So we'll see that you need some pseudo-random because it simplifies the key exchange on both sides. Okay, so we'll break for Okay, so for these random generators, we can use two types of these deterministic algorithms. We can design our own, which is what we call purpose-built algorithms for generating this random sequence. Okay, and we will talk about an example in the upcoming slides, which is used for RC4. So RC4, as a stream cipher, it actually uses certain seed or key to generate some random sequence, and then it uses verinum cipher. Very, very simple. So this algorithm is purposely used for generating a random sequence, deterministic algorithm. We'll talk about it. Or we can use some cryptographic techniques, okay, as the random generating algorithm. The only thing here is that we don't have to have reversibility. So we can use the encryption on both sides. Okay? The encryption here will generate random sequence. The encryption here will generate random sequence, and supposedly the two random sequences will be the same. We don't have to decrypt in that case. ماشي? We just use the encryption algorithm or the cryptographic technique to generate random sequence. But we have to apply the two conditions on the generated output. Lower in that case would be the ciphertext. Okay? So, these cryptographic techniques can act as a pseudo-random number generators. Of course, they are not true random source of. So they have to use a key, which is in that case is in replacement of the seed. Okay. So this can be symmetric block ciphers or asymmetric block cipher, whatever. Okay. So we can use, مثلا, the encryption on RSA, which is the public cryptography. We can use it as a random sequence generator. Okay. ماشي. We can use برضو hash functions. We'll talk about hash functions. We didn't talk about hash functions here. طيب. So this is the end of the block ciphers, and the random generators are used as part of the stream ciphers. So one of the use cases for these random generators is to be used for stream ciphers. As we said, stream ciphers, unlike the block ciphers, what we do here is that we use some deterministic algorithm to generate stream of bytes. And then what we do is that we take one byte from the input plain text, we XOR it with the byte from this algorithm, and the output will be 1 byte. Okay? The difference here is that this does not have to have a block size. So the plain text is like stream of bytes, okay? And we need to generate another stream of random bytes, okay? But this stream of random bytes is based on the key, okay? The stream of random bytes will have as long size as we want. So we can use the same key to generate forever random bytes. ماشي? Theoretically, we can generate random bytes as long as we want. ماشي? Based on the key. Okay? And for stream ciphers, the plain text does not have to have a specific block size. It's not by 64 bits or anything. It's just sequence of plain text.
But we have to deal with it, process it as byte by byte.
Byte by byte, yes, byte by byte. Okay, type. Some properties of this stream cipher as opposed to the block cipher. Okay, because if we have, assuming that we have a transmitter And this is the exact scenario that we'll talk about in the assignment. Yeah. We assume that there is a transmitter, and this transmitter uses different types of ciphers, whether it's block cipher or stream cipher. Okay. Type. So the transmitter, if it uses some kind of a block cipher, then we'll end up with ciphertext. And this ciphertext will be blocks like this. Okay? For the block ciphers, the output will be blocks of ciphertext, right? Assuming that you have a channel in the middle, what will reach to the receiver, okay, is this cipher blocks, okay? But there is some kind of effect that gets introduced by the channel. And that's not necessarily a tag. Yani if you assume that you transfer these cipher blocks over wireless, which is the exact same case that we'll do in the assignment, okay? Wireless channel has certain effects, has certain impairments, and this may, in fact, affect small part of some of these ciphertext. Okay? The idea here is that the block ciphers, although they introduce very robust and strong security aspect, it's very intolerable to the channel manipulation. Okay? In other words, if there is some manipulation to the one of the blocks, okay, the effect that you will get here has no correlation with the plain text house. Why? Because in the block ciphers, what we have discussed is that this block cipher is a result of many permutations and operations and stuff like that. So any small change, if you have one bit manipulated, the result in the decoded plain text here will be enormous. Okay? So any small change will propagate the error on the receiver side. واضح كده؟ Okay? In other words, this will, if we are using مثلا TCP for transmission, and assuming that we will detect the fact that there is one bit manipulated, then this will lead to lots of retransmissions. And that's why TCP, as we said, in networks, it's not tolerable to any errors, because you have to repeatedly retransmit and everything. Okay? So that's one property in block ciphers. تعال نشوف بقى in stream ciphers. In stream ciphers بقى, we will generate sequence of ciphered bytes. Okay? Which is the result of result of هنا, what is this? Vernam cipher. Okay? So if there is any manipulation in the middle, okay, and then you decode this, you will find very high correlation still between this and the actual plain text. So the effect of this manipulation will be localized. Why? Because here I'm doing simple XOR. Right? واضح? Yeah, it's not like permutations, it's not like this. ماشي? So as long as you are using, so this output is generated locally, and all you do is just to XOR. Okay? So any manipulation here, which means that طبعا decoder on the other side, based on what? Based on generating, the decoder will generate the same random sequence and will XOR it again. That's it. So XOR 2 times will produce the original text. Right? So any manipulation to the bits by the channel, the error will be localized. The error will be local. The effect of this error will be local. Unlike البلوك سايفر. واضحة النقطة دي؟ So this is actually the motivation why they came up with what we call the operation modes for the block ciphers. So one of the motivations is to try to get the security strength of the block ciphers with the tolerance to bit manipulation of the stream ciphers. And we'll see how they did this.
Can we transmit the block cipher as a stream so we can
هو بالأخير it's a stream of blocks. It's a stream of blocks.
transmit it as stream of bits?
You can, yes. You can. There's no problem. But the problem here is that if there is one bit manipulation in any of the blocks, you lost the whole block.
Now it's not block. It's a stream of
Here, it's not a matter of whether you transfer it as a stream or you transfer it as a block. The problem is that the block ciphers, they have to work on one block, okay, and create a cipher block, which in fact has no correlation with the plain text whatsoever. Because it's based on many manipulations and permutations and so on and so forth. So if there is one manipulation to one bit, you will not be able to decode and get the plain text in any way. وانت هتشوفها في الأساينمنت. يعني basically كده I'll give you a picture. Give you a picture. ماشي? You transfer this picture over a wireless channel. If the channel is perfect, you will decrypt the picture on the other side. You will see the picture looks very nice. Okay? So now the channel has 10 to the power minus 10 probability of error. And you will see what is the effect of this on the image itself. With a simple error, يعني مثلا if the error is like 2%, 3%, it will be very, very clear on the image. You will not be able to see it, the image will be corrupted. Okay? Apply the same probability of error on the stream ciphers. You see that the image is almost not changed. No change to the image. Why? Because the error is localized. There is actually an error. If you zoom in, you will see that some pixels have been manipulated. You will see that. But if you zoom out and see the picture, it's not visible. That's based on the fact that block ciphers, they do lots of manipulation to the block. The block is the result of many recursive manipulations, permutations, expansion, things like that. So any error will propagate in the entire block. Stream ciphers, لا. Stream ciphers is based on what? Is based on generating the same random sequence on both sides, and then you just XOR. Okay? When you get XOR, ماشي, between X and Y, okay, you will get Z. If you XOR Z with Y, you will get X. ماشي? So 2 XORs eliminates the effect of XOR. خلاص. So here, the decryption is based on XOR. That's it. You generate, this is not decryption. It's not a decryption per se. It's just generating the same random sequence, okay, and you just XOR with the ciphertext. You get the plain text. And that's why the effect of any error here is localized. And you will be able to see that visually. Okay? So that's a very important property of ciphertext, and this is actually the motivation of the cipher modes of operation. Cipher modes of operation, which we will talk about.
Later, I have a question. The stream of ciphers will not produce an overhead on the reception side because it's a stream?
The stream of ciphers.
Will not produce an overhead on the reception side?
Why?
Because it's a stream. So
No. هو actually the blocks, as Ahmed was saying, the blocks, يعني هو when you transfer things over the channel, the physical layer will convert everything to bits في الآخر. فهم eventually, whether you want it or not, at the end they will be transferred as bits, raw bits. ماشي? In fact, not raw bits, it's actually signal, analog signal. whether you accept it or not, it will be transferred at the end of the day as analog signals. ماشي? Whether it's bits ولا bytes ولا at the end of the day it's signal, analog signal. ماشي? But there is no overhead on the receiver whether I transfer this in byte sequence or blocks. It doesn't matter because at the end of the day, what you are receiving is actually an analog signal on the receiver. الفكرة بقى when you go بقى from the physical layer all the way up, will you get the same data? What I'm saying is that for the case of the block ciphers, you will not get the original data. What you will get is a corrupted data, even if the manipulation is very small in the block ciphers. At least until the techniques that we studied. And we'll see how we modify this. Another يعني property here, which you have to pay attention to, is the effect of synchronization. Effective synchronization. ماشي? Because if I give you the same seed, which is the key, and the same deterministic algorithm to generate a random sequence, okay? So the random sequence that you will generate is like A, B, C, D, and so on. Okay? Something like that, right? And if you get the same key here, okay, you will get A, B, C, and so on. صح? If there is any time shift, okay, if there is any time shift, and what you generate here is like the first letter مثلا you don't take, and you take this, خلاص انت you lost synchronization. Which means you will XOR the incoming text with another. It's still a random generated text. It still applies the two conditions and everything, but the synchronization has to be achieved. The two random generators, they have to start working at the exact same time in order to generate the same random sequence in order to get the actual plain text, the actual plain sequence on the other side. So there is a synchronization issue. ماشي? We didn't have to do that on the block cipher because the block cipher, it's blocks by blocks. Yeah? Blocks are supposed to be stored in a queue, and then you take block by block. خلاص. And then here we can apply on the byte level. It's byte sequence.
Local problem or because the whole stream?
Yeah, the whole stream will be يعني, yeah, the effect of the error will be huge. But طبعا the synchronization is not to say no, it's not solvable. Synchronization techniques are يعني, very well established nowadays. So we can assume that they are in sync. Yeah. But as long as they are in sync, you are using the same key, you will be able to produce the same random sequence, which means that you can reconstruct the plain sequence on the other side. There's no problem with that. But it has to be for the
Applications that can apply stream cipher.
applications. We'll talk about security services and wireless. They still use RC4. They still use RC4.
Any network transmission, right? These stream ciphers apply in all network transmissions.
And network transmissions, but she's talking about a specific example. A specific example, we call it a web. يعني حتى if you go to your wireless router at home and you see the configuration, you will see that one of the choices, whether you want to do your wireless network نفسها, whether you want to use no security or you want to use web or WPA1 or WPA2 or something like this. We'll discuss all these issues in part 2. ماشي? Web uses RC4. Web uses RC4. And that's why it's easily breakable. Because here, I have to say that the cost of this is that the security strength is very low. Why? Because as we said, it's based on Vernam cipher. صح? Vernam cipher, as we said, as powerful it is, the Vernam cipher, you say that the cipher text equals to the plain text XORed with the key, except that this key is actually the random sequence generated. Okay? ماشي? So there is, as I said, if you assume that the attacker only knows the cipher text, Vernam cipher is actually very good. And they prove that using information theory. They say that the probability of having مثلا the probability of having certain the probability of having, if knowing the certain ciphertext, okay, that the key equals to a certain key I, knowing CI, okay, the probability of the fact that the key takes a specific value, given that I know the cipher, ماشي, they proved, again using some probabilities, that this is equal to the probability of having the key equal ki. Which means what? Which means that knowing the CI does not change anything. Does not change the equation خالص. So if you know only this, the cipher text, in fact, you didn't know anything. If you add to this knowing CI and PI, then the problem becomes trivial. Why? Because the key is simply PI XORed with CI. So I know one CI and I know one PI, so the key is actually the XOR between them. That's it. So I got, in this way, I got the random sequence. خلاص, I knew that. Okay? So even with web, it does not, it actually uses other things. It's modified. It's not exactly like this. It uses some kind of initial vectors and stuff like that. But even then, it's very breakable. It's very easily breakable. Okay? But there are certain systems that use RC4. ماشي؟ طيب فهمنا So the stream cipher design considerations here is that encryption sequence have a large period of time. So هنا we are not restricting the length of this random sequence. It can take as long as we want. صح? It's theoretically infinite. Practically لا يعني if you start generating a very long random sequence, okay, you will end up breaking the conditions that we talked about. Okay?
You start repeating yourself.
Yes, you start repeating yourself. ما أنت خلاص, you're not. It's not like you cannot innovate anymore. I give you a very short key and you generate infinite sequence. مهما كنت يعني at some point you will repeat yourself. Okay? So it's not advisable that you generate a very long stream sequence. ماشي؟ طيب. The key stream should approximate the properties of a true random number, as we said, which means that it fulfills the two numbers. The pseudo-random number generator is conditioned on the value of the input key. Again, so if you want to increase the length of the generated sequence, increase the length of the key. Okay? By increasing the range of the length of the key, you'll be able to generate longer random sequence. ماشي? This is the RC4. It's a stream cipher which is designed in '87 by Ron Roberts law for RSA security. And it's variable key size, variable plain text. No restrictions on the key size or the plain text. ماشي? Currently, as I said, it's used as part of the web, as I was talking to Shema, ماشي? Which is used as part of which can be used also as part of SSL and TLS. But it's TLS and SSL, they deprecated the use of RC4 long time ago. It's not being used anymore. Currently, it's being used in web, which is still used as an option in some of the wireless routers until nowadays. Okay, and it's easily breakable.
Why is that?
Why is it breakable?
No, why is it used? It's that easy breakable.
قول لهم. يعني هو if you use that for a wireless router at home, obviously يعني security is not, it doesn't have to be very strong. You don't have attackers standing outside your house waiting to break you.
What are the benefits also to choose this?
Eh?
What are the benefits?
It's simple. It's very simple.
It makes it faster, مثلا.
Yeah, very fast. As you can see, it's very fast. You'll see that in the assignment. Very fast. Very easy to implement, very fast. So adding some complexity overhead here will reduce will reduce the time, will increase the time, will increase the complexity. Sometimes for no reason, maybe in your house you don't need that very high security.
No, some applications, like some use cases, for example, the wireless client, is not compatible with the WPA advanced encryption key. So some big
Sometimes yes.
all devices
Right.
still only
صح, that's a good issue. Sometimes you need to set the wireless router عندك to web, because you know that there are some devices which does not understand anything other than WAP اللي هو الويب. Okay, these devices, they don't have the capability to use WPA or something like this. In any way, so the way that RC4 works is basically, as we said, هو أصلا this whole thing is to generate the stream, يعني generate the random stream. Okay, because after this what we need to do is just wait XOR. Yeah, there's nothing to it. But the way we do this is that first we have the S vector. The S vector contains all the 256 characters that we have from 0 all the way to 255. اللي هم ال UTF-8 اللي هم ال ASCII characters يعني. Okay? And then if you have a key, okay, what you do is that you generate like an initial state vector T. And T is nothing but اللي هو ايه the TI equals to KI mod 256. That's it. That's it. Okay? So it's like the first item هنا will go to T0 and T key length and T2 key and so on. You will repeat the key multiple times. As long as you want. ماشي اللي هم until 256. Sorry, not as long as you want. Until the 256 finish. ماشي كده? So this is, we call this the initial state. And then we perform initial permutation. By permutation here we mean a byte swapping. Byte swapping. And this initial permutation step has a fixed length. ماشي? Initial permutation step has a fixed length. All we need to do here is just to take this T, okay, calculate J plus SI plus TI equal J. And then we take this J to be the index in S and we swap I with J. That's all. Okay? And we do this for fixed number of times equal to 256. Until now, we did not generate the random sequence of bytes yet. Okay? So the initial permutation step is of fixed number of iterations. Okay? The second one بقى is called the string generation. Okay? We take this S and then we apply another permutation step. This time بقى while true. While true معناها ايه؟ It's forever بقى خلاص. As long as you need, you can generate bytes based on what? Based on اللي هو J equals J plus SI. ماشي? And then you swap SI with SJ and then you take that byte output. Take that byte output. So every time you do this swapping and you output the current byte. Okay? And this will be done while true. So these are these two steps of permutation. Initial step is of fixed size. The last step is for variable size, forever. ماشي؟ طبعا given بقى these steps, the assumption here is that the generated byte will fulfill the two conditions we talked about. Theoretically, if you do these steps, the output is guaranteed to fulfill the two conditions we talked about: randomness and unpredictability. ماشي؟ Generating these random bytes, we XOR and that's it. ماشي؟ You will see the implementation of RC4. It's very, very simple. In Python you can do it. لو قول بس ChatGPT قول له بس generate random sequence using RC4 طلع لك كود كده. That's very simple. ماشي؟
I didn't get the last one. How it could be infinite size or is there limited size?
J بقى هنا يعني هنا from 0 to 256 or 255. this one is fixed. ماشي. The second permutation is while true. So J every time changes. J every time changes. And I is the current location that you have. ماشي. So at any point of time we say calculate J ماشي based on this simple equation. Okay? Then get the index of Sj in the location that you have and output the byte.
But if the location is not exist or it's up.
It cannot because everything is mod 256. Oh, that's the key بقى. Everything is mod 256. Always mod 256. ماشي؟ فيو can never لأنه أنت عندك الألفابت is limited يعني 256 فهو they use the ASCII characters. ماشي كده؟
What do you mean by mod 256?
Mod 256 in the index cannot exceed 256. يعني 257 mod 256 is what? Is 1. صح؟ 256 mod 256 is 0. Right? So this index J always goes between 0 to 255. Always. It cannot go beyond that. So all these operations are mod 256. Always. If you don't know the modulus arithmetic, you need to review that thoroughly in linear algebra and all these things because in public cryptography يعني it will be يعني much more complex. ماشي؟ بس عايزين نخلص البتاع ده قبل ما فالcipher block modes of operation, as I said, the symmetric ciphers process one block at a time. In cipher modes of operation, what they do is that instead of doing it block by block independently, what they do is that they do it in a pipeline fashion. In a pipeline fashion. So they get the cipher text from the previous text, and they put it as an input to encrypt the next plain text. I told you why. Why do they do this? The motivation is one of these two possible motivations. If you do the mode of operation in a pipeline fashion, then your objective is to strengthen the security even more. Because encrypting one plain text will not only be based on the key in that case, but will be based on the key and the previous ciphertext. Okay? ماشي? So this increased dependency increases the security level even more.
This is the blockchain idea, right?
عاملة زي البلوكتشين idea, yes. Yeah, لا هي it uses the same idea, but it's not blockchain. لا, it's not blockchain. ماشي? The other objective we'll see is to use the strength of the block ciphers, but to generate an output which looks like a stream cipher, and that's what we need to discuss here. So, طبعا there are many of these, but I selected 3 of them. The first one is called cipher block chaining. Cipher block chaining. So instead of taking the plain text only, if you look at any stage here, you will see that before we encrypt the plain text directly, we get the ciphertext from the previous block and XOR it to again increase the unpredictability of the plain text. encryption ممكن يكون this أي حاجة بالضبط كده. ممكن يكون أي حاجة. In the assignment we will use cipher. Yes, exactly. Yes. For cipher blockchain is very easy. It's just to take the same block cipher, is to do it in a pipeline fashion. And supposedly by doing this, we increase the strength of the security even more. Okay? Very simple. What about the first block? In the first block, we use by because we don't have a previous cipher text. Okay? So we use what we call a initial text. Arbitrary, يعني some text arbitrary. ماشي؟ فcipher text 0 is initialized to initial. Very simple. ماشي? By doing this, we increase the strength of the security, but as you can see, we add some overhead. And not only that, you will see in the assignment that if you do the cipher block chaining, the effect of manipulation from the wireless channel will propagate to all blocks, not only to that block. So the effect on the image will be huge. صح? It's obvious. So one effect on one block, one bit manipulation on one ciphertext will affect all the upcoming ones. صح؟ that's يعني that might be looked at as a disadvantage. But here the objective again is to increase the security strength. Cipher feedback mode is a different mentality. The requirement here is to use a plain text, okay, of S bits, and this could be like only 1 byte, which tries to get to more into a like stream cipher. Yeah, we can take the plain text like part by part, small part by small part. Okay, and then we don't apply the plain text to the encryptor. لا, we apply arbitrarily text, initial vector, which means that the effect of this is that, in fact, what we are doing here is that we are generating a random sequence based on the initial vector by using the initial vector as a seed. مش احنا قلنا ان الانكريبتور can be used in replacement of the random generator in a way. Okay, so here we don't apply the plain text, we actually apply some initial vector. So it's like we generate a random sequence, and then we take only the first S bits of the random generated sequence, and we just use the Vernam cipher to produce the ciphertext. So again, the objective here, unlike the previous one, is just to use this cipher feedback mode as a way to use the block encryption techniques in the form of stream ciphers. Okay? But then we use some block chaining as well. So we go to the ciphertext here, and then we apply it to the initial vector to do some shift to the initial vector. And then we do the same operation again. So every time we shift the initial vector by S bits, and we apply and so on. So the generated ciphertext here can have a length similar to the plain text, which could be like 1 byte. Okay. Here, it will have the effect of stream cipher, and you will see that in the assignment. But here, the overhead is huge, because I'm generating a big random sequence, and every time I'm taking only a small part of it. Okay. So if you have a plain text which is very long, the overhead here will be very high, and we'll be able to see that. Okay. The Thorn tries to achieve the compromise between the two. It's like having really a good trade-off between the two. And really the counter mode is really very efficient. Very efficient. So, and it will have almost the exact same effect of the stream cipher. If you look at the structure here, you will see it very, very similar, in fact, to the RC4. Very similar. ماشي? So here the counter mode, this counter mode, that's counter 1 معناه ايه؟ It's like an arbitrary chosen counter, and then you increment by 1. So which means that this is like arbitrarily selected text. You apply it to the encryptor using the key, it will generate some random sequence, and then, here, you generate a random sequence, and then you XOR it with the plain text. That's it. And if you do this again here, and you XOR it again with the ciphertext, you get the plain text. So this is the encryption, and this is the decryption. So if you look at this, you see it quite similar to RC4. And in fact, the output will have the same properties of RC4, except that using the block ciphers will make it, from a security perspective, will make it strong. So counter mode is supposed to have the same performance and same properties of stream ciphers, while having the strength of the block ciphers. Okay? You will experience that in the assignment. All these techniques will become easy to and you will be able to analyze command. Analyze from the perspective of the error properties and performance-wise. Basically, you'll put timestamp before and after. You calculate the time required to do encryption using RC4, using اللي هو الcounter mode, using DES, triple DES, AES, things like that. It's block cipher having the effect of the stream cipher. يعني the same effect معناها ايه؟ Same properties. بمعنى if I apply some bit manipulation to the cipher text here, okay, and then I try to use this cipher text manipulated to get the plain text, the plain text is gonna have an error which corresponds to this error. It will be localized. So the error will be localized here, here, and here. If you apply this to an image, the effect will be 1 pixel changing, which in your naked eye you will not be able to see. Imagine?
And here there is no correlation between the...
And here there is no correlation between the cipher text and the original text in any way at the encryption level. Okay? So the security strength here is high, and the actual effect, it's still block by block. صح. It's still block by block. But when it comes to error properties, it has the same error properties like the stream cipher. Okay? But still block by block طبعا. ماشي؟ Because احنا قلنا طبعا at the end of the day, whether it's blocks ولا bytes, it will get في الآخر ايه transferred as analog signal. صح؟ But the key thing is that if there is an error, will it be tolerable to this error or not? The key thing is, what is the performance in terms of speed? Okay, what is the performance in terms of speed? Obviously, for this one, it will be slightly more than RC4 in terms of speed, صح? But you will see it's not, because if you use here AES, okay, you will see that this is quite comparable to the RC4. The difference is very small in terms of performance, but in terms of strength, it's high. And the error properties is the same, similar to stream ciphers. ماشي؟ واضحة؟ بقول لك أنا الأسايمنت يعني will make things much clearer يعني. Assignment will make things much clearer. Yes.
ده هيأثر على البلوك ولا هيأثر على البيت؟
هيأثر، ما هو ال 1 bit manipulation here, which means 1 bit manipulation here, and you will see that the error here is also 1 bit. Okay, the problem is that if you don't do it this way and use the previous block ciphers, 1 bit here, if you try to decode it, the effect will be on everything. Why? Because you don't actually use the Vernam cipher directly. What you do here is that you have to do lots of permutations and manipulations and matrix multiplication and so on. If you use the original decryption using DES or AES, right? So 1 bit manipulation will correspond to many bits being in error in the case of traditional block ciphers. But here you will see that the effect of error is always localized, which is an advantage. واحد يقول لي طب ما blocking error, what is the problem? Okay, I will detect that there is an error and I will remove this block and I will ask for retransmission. Yes, you could do that, but some applications they don't have to do retransmission. They don't have to use TCP. ماشي? In that case, this will be much more efficient. I don't have to actually use any kind of retransmission ولا error يعني error techniques ولا حاجة زي كده. خلاص أنا error خلاص هتعامل معاه. I'll deal with it. And the effect of the error, especially in multimedia applications, they are very tolerable to the channel errors. Very tolerable. But they are not tolerable to delay. In these types of applications, these types of cipher techniques are very efficient. عشان كده الcounter mode, you remember this name, الcounter mode, you will see it applied in many security services in part 2. Remember that name. ماشي. So that's the end of the of this. طبعا يعني the effect of the cipher mode اللي هو counter mode, it can be done in hardware, it can be done in software. Pre-processing is based only on XOR. It's very efficient. طبعا the proof of randomness is provable even using AES or triple DES. Both of them, they can be proved to generate random sequence that can be used as part of the counter mode. ماشي? In addition to simplicity, and by simplicity here we mean that it's very simple because it's based only on XOR. But the property which what we talked about is that it's also tolerable to channel manipulation or tolerable to errors. ماشي? So this is a summary of this chapter. I wanted to just finish this chapter. So we talked about the symmetric cryptography. We talked about the cryptographic types, the different types. We talked about the physical structure and the properties of that. We talked about block ciphers and stream ciphers and the random generators. We talked about the modes of operation. We talked about these 3 modes of operations having the motivation of either strengthening the security aspect or having the properties of the stream cipher, ماشي? In terms of error tolerance. ماشي كده? Any questions?